we saw this. We saw how you can you can join these mean terms to get the various nodes in this lattice, and we also saw I mean these are really syntactic aspects, but this one there is a logical component over here. So what is being said here is this part we are looking at. So P1, let us say P1 P1, let us say, is x, y, z bar. Okay. Sorry, x, y, z bar. And it is included in P2. So P2 is, let us say, x, y. So we are saying that P1 is included in P2 if P2 has all the literals of P1. A fundamental product P1 is contained or included in P2 if P2 has all the literals of P1. So if you see, P2 has all the literals of P1. It has x, it has y. Alright, it has all the literals of P1. So now one second. Contained in P2. A fundamental product P1 is contained or included in P2 if P2 has no, just a minute. I think this one will probably just a minute. If P2, yeah, if P2 has all the literals of P1, so yeah, so P2 has all the literals of P1. So it is saying that fundamental product P1 is included in P2. Okay, so yeah, so this is of course the terminology, but so here, as you can see, here P2 implies P1. So yeah, this terminology is a bit, you have to be a bit careful. So, but basically, what you have to understand is that this xy is actually, I mean, although this has as a string this is longer, but this actually is bigger than this. Why? Because xy is equal to xy times z or z bar. All right, that is equal to xyz or xyz bar. All right, so so basically this one covers something more. It covers something more than this. All right, so what you can see, so this part is P2, and this P1 is really this whole thing. This whole thing is P1. So what you can see is that whenever P2 is true, P1 is going to be true. That's why you have this implication that P2 implies P1. All right. So that is yeah, but yeah. Just be careful about. So this one is saying that P1 is contained in P2. So this is, I mean, this is just contained as a string. Okay, it is contained as a string, but logically, this is it is really P2, which if you look at the mean term, if you expand it, this is not necessarily a mean term. If you expand it, then you find that this product is actually logically bigger than this product, but as a string, this is contained in this. So that is what you have to be a bit careful about. Anyway, this is just a terminology, but this is the idea. All right. So, so a sum of product expression is it's either a single product or sum of two or more fundamental products. So this is an example of a SOP. Okay, this is an example of a SOP. All right, and all of these are fundamental products. All of these are fundamental products. Okay, this one, this one, this one. These are all fundamental products. Okay, these are just syntactic terms really. All right. And of course, this De Morgan's laws and means other you know uh, uh, other properties may be used to simplify Boolean expressions. Okay, we'll just touch upon another topic which we shall see in more detail later on. So, one question is which Boolean operations are, what is the minimal set of Boolean operations that you need to express any Boolean function. Okay. So, the inspection of the Boolean lattice gives you some idea, of course, because what you see is that your atoms, what do you need to express your atoms? To express your atoms, you need the, meet, or you can say the AND operation and the complement operation. Okay. And the complement operation. And all other nodes can be expressed as the join. Join means plus. So these three, and, not, and, or, using these, as you can see, you are able to express all the Boolean functions. These are just short forms. Alright, these are just short forms. This is also called equivalence. Means this is true when A and B have the same value, and this is Of course, the opposite of this is exclusive OR, but it is also the opposite of equivalent. This is true only when A and B have different values. All right. So these are. So we have seen about AND, OR, and NOT. Now NAND is also considered to be functionally complete. So can anyone say why NAND should be functionally complete? Well, first of all, before we go on to NAND, what about so you can say what is all right. So so you can see that this OR is also extra because you can write X or Y as all right. So this OR is also extra. So what you find is that and not so OR can be expressed using you can say and not, right? So similarly you can express and using or and not. Are you okay with that? Now this is NAND actually. This is NAND. Alright. So what you find is that alright. So using NAND you can of course realize NOT. Alright. And also so you can realize NOT. And what is NOT of NAND? Is AND. Alright, so as you can see, using NAND, you can realize both NOT and AND. And NOT and AND is enough. Because using NOT and AND, you can realize both. You can realize OR also. So as you have seen, you can realize all the Boolean functions in a lattice using AND or NOT. So that establishes that NAND is enough. If you have NAND, that is enough. You can compute. You can realize any Boolean function with just NAND. Is that okay? So can you just work out in your notebooks that you can do I mean, NOR is also functionally complete. Can you work out in your notebooks that way? Hello? Just work it out in the same way. Are you doing it? Hello?
Yes, sir.
Yeah, just do it. I mean, it's a simple exercise. So NOR is also functionally complete. Yeah, I'm in a class now. Can you talk? Yeah, good morning. I'm in a class now. We'll talk later. No, I'm in a class now. Yeah, okay. I'll talk to you later. I'm in a class now. Okay. All right. So this is about NOR. Now, interestingly, you can also use XOR AND. XOR AND is also functionally complete. But can you so can you figure out how you can compute, say, NAND using XOR AND? NAND or any I mean, um, oh, okay, AND you have already got. So if you can compute NOT, that is enough. You have got AND. So all you need to show is that if you can compute NOT. So using XOR AND, can you compute NOT? Why don't you just try it out?
So X is or 1.
Sorry?
XOR with 1.
Yeah. But there is also a point to note that this characterization was a little loose in the sense that, as you have just said, you need a 1. All right, 1 is also a Boolean function really, which is always true. So you also need 1. Sometimes, loosely speaking, sometimes that is not explicitly mentioned, but you do need a 1 to uh, to uh, realize not. So in fact, uh, we'll see how we can analyze the functional completeness of a set of operations. We'll see that later. But uh, uh, that's an interesting observation. See, if you are given a functionally complete set, it's not so difficult to show that it is functionally complete. But if your set is not functionally complete, it is not so easy to show that it is, I mean, something is lacking. Because, I mean, you can always say that, there may be some way to combine those functions to, make them functionally complete. So, yeah, so that argument is a lot more difficult. This is an interesting function. You have already studied a multiplexer. So can you work out how you can, so multiplexers are also functionally complete. So can you work out how you can realize other functions using a multiplexer? So can you realize the AND gate using a multiplexer? Can you realize an AND operation using a multiplexer, for example? Or for that matter, NOT. Can you realize NOT using a multiplexer? Or NAND, whatever. It is enough if you realize the NAND function, because we have seen that NAND is functionally complete. So can you realize the NAND operation using a multiplexer? Yeah? Can you try? Can you try to realize NAND using a multiplexer? Okay, let us see.
Sir,
Yeah, tell me.
sir, we can sir set the values of s to something. Can we do that?
Sorry?
Sir, can we do something like we can set s equal to x? Is it
No, see,
allowed?
I'm just doing it. You just see. But again, there is a little catch. So what is the truth table of NAND? So whenever any one input is 0, it is alright. So if you so now again that is the catch. So this realization we needed constants, this Boolean constants. Alright. We needed Boolean constants 0 and 1. So if you have the multiplexer and Boolean constant 0 and 1, you can of course realize the NAND function. Okay, so you can also realize NOT in the same manner, but again you need these Boolean functions 0 and 1. Alright, so when x is 0 you give 1, when x is 1 you give 0. So this is NAND. This is NOT. So this way, of course, you can, I mean, you are really, just realizing the truth table. All right. Now, if you have the complemented variables available to you, okay, if you have the complemented variables available to you, so can you, so suppose you have you have the complemented variables. That means you have got x, you got x bar, you got y, and you got y bar. In other words, you have you have the facility of complementing. So if you have multiplexer and NOT, then can you give this thing? Can you give a implementation of NAND using a 2-to-1 multiplexer?
sir, can we use 1 and not y as inputs?
Yeah, so let us see. So say you have x here. So whenever x is 0, you know that the output is going to be 1. Alright, whenever x is 0, sorry, whenever x is 0, the output is going to be 1. When x is 1, what will be the output? Output will be y bar, right? So if y is 0, the output is 1. If y is 1, the output is 0. Right? So this is also NAND using so I mean, strictly speaking, your marks 0, 1, this is functionally complete, or as you can see, marks not 1. This way you can realize NAND. So this is also functionally complete. All right. Now, so as you can see, it is possible to do that. Let us just see. Random access memory. So can you comment on the completeness of a random access memory? Any thoughts? Yeah. It is very simple actually. It is because you can remember the truth table, right? So how does a random access memory work? So suppose you have a memory with, let us say, memory of 4 bits. Suppose you have a memory of 4 bits. Alright. And you have got address lines X and Y. So you have got 4 locations, right? You have 4 locations which can be addressed by 2 bits. What are the addresses? 0, 0, 0, 1, 1, 0, and 1, 1. So random access memory, what does it do? I mean, whatever is stored here, that you will get as output, right? Whatever is stored here, that you will get as output. So this is your address, let us say. And this is your data. Of course, random access means data is really two-way, but so now consider the NAND. So what you want here is you want 1, 1, 1, 0. So if you want to program, so there is a programmable component. If you want to program it, so this one also has, it also has a read-write port. Read-write means read-write, it simply controls whether you are going to read from the memory or you are going to write to the memory. So if read-write is 1, then you are going to read from the memory. If it is 0, you write to the memory. So so if you give so if you want to program it, basically at this address at 00 you'll write a 1, at 01 you'll write a 1, at 10 you'll write a 1, at 11 you'll write a 0. So that's how you program this memory, and then you put it in the read mode. So whatever you give here, you will get the corresponding value, the function value here. So that makes random access memory also functionally complete. Is that okay? And of course, to be more, to be more precise, it is not just a RAM. So RAM is, I mean, if you think of it functionally, you need, RAM 10 daily. That's what you need to use the RAM as a functionally complete module. There is another, it's a minority gate. Minority gate gives you the minority value among given inputs. So, so I'll give it to you as a small exercise. I mean, you can work it out on your own. So, functional completeness of the minority function. You can just work it out on your own. Functionality of minority. I mean, I think you can do it. It's not so difficult. Just try it out. Also, this, both of this you. Okay, this one you have already seen. This one you have already seen. So, this one you just try and around. All right. Okay. I had this in my slides. I'm not very sure I had written it. But anyway, do you think it is possible to simplify this Boolean expression based on what you have done so far? Is it possible to simplify this Boolean expression a bit? Yeah. Can you just try? Just try and someone can tell me, like, what's a simplified form?
X z bar plus y bar z.
Yeah, you could say x z bar plus y bar z. I think, yeah. Okay. Yeah, that's all right. So others can also just, make sure that you're able to do it. All right. So, all right. So a sum of product, you know what a sum of product is? So a sum of product where each, each term, we can just call it a term, but if you want to be a little, if you want to go by the syntactic expression, it is called a fundamental product. So where each term or each fundamental product is a mean term, that is said to be in disjunctive normal form. Okay. Now this disjunctive normal form, we'll just say it as, yeah. So the disjunctive normal form of any sum of products is unique. See, when you are given, say you are given two Boolean functions, all right, you are given two Boolean functions, of course, on the same set of variables. Now you might like to know whether those two Boolean functions are equivalent. I mean, whether those two Boolean functions, that means they produce the same output for the same input. So, how can you do that? Or is it even possible to do that? So, one way is that you can evaluate. So, I mean, this is suppose you have f1 and f2. So what you can do is, if it is defined on x1, x2, so on, xn, then you can construct a truth table, right? You can construct a truth table. And you can also, f1 and f2. So you can, for the various entries, you can tabulate the values of f1, you can tabulate the values of f2, and check whether the two are indeed the same. So it is possible, okay, except that it's a bit expensive. What is the cost? It is theta to the power n, right? So it's an expensive procedure. I mean, if you do it this way. In fact, it's not very easy to compute two functions. That's now. So this requires you to evaluate these two functions. You need to evaluate these two functions. Can you do it without evaluating the functions? All right. So one thing that you can do is, one thing that you can do is, you can express the function as, disjunctive normal form. So how do you do that? So suppose you have x or yz. So is this a disjunctive normal form? Is this a disjunctive normal form? Hello? Is it? Yeah, can someone tell me? I mean, the answer is quite simple, but at least you can tell. Yes or no? Hello? It is not, of course, but you can, I mean, it is not, because these are not mean terms, right? These are not mean terms. It is not a disjunctive normal form, no. Can it be converted to a disjunctive normal form? Yeah?
Yes, sir.
Yeah, so you can convert. So you can convert it this way. So you can write it, and here you can write so this gives you xy. Of course, now this one will so this one is a disjunctive normal form because all of these are mean terms, right? All of these are mean terms. So now, I mean, it is not hard to see that the disjunctive normal form is unique, alright. I mean, we have already studied the proof. Can you relate to what you have already studied? These are atoms, right? Each mean term is an atom, and as you have seen that any element of a Boolean lattice has a unique representation in terms of mean terms. So it has a unique representation. I mean, unique up to permutation, of course, but it has a unique representation of in terms of the mean term. So you have already studied that proof. You have already studied that when you studied lattices. So this gives you a way to compare two functions again. So f1 you have DNF of f1, and from f2 also you have got the DNF of f2, and you can compare them. Of course, the time complexity is still exponential, but it's just a different approach. So this is a symbolic approach. Here you are manipulating the expression symbolically. Okay, so and there is also another just as you can express in terms of mean terms, you can also express in terms of max terms, because as we said that this lattice is a very symmetric structure. So what you can these are the max terms. So as we said that just as you have you have a joint representation, joint rep using mean terms, you can have a meet rep using max terms. It is exactly the dual. One is the dual of the other. All right. So just as you can express an element as the join of the mean terms, you can also express them as uniquely as the meet of the max terms. It's exactly the dual. One is the dual of the other. All right, I think we can stop here today. Okay, but so
yeah.
No.
So what do we do next week?
Yeah, that's what I'm asking. So you can tell us. So what is the directive that you have received for next week?